Okay, in the last we have discussed about the magnetic field and magnetic field pattern due to current carrying conductor as well as current carrying loop. And today we will discuss about magnetic field expression of magnetic field.
रुको मैं क्लास कर
हेलो, सभी लोग अपनी मोबाइल को म्यूट कर लोगे और if you have any questions then you can ask me question. Okay, so today we will discuss about magnetic field due to current carrying solenoid. In the last class we have discussed what is solenoid. You see here this is the solenoid. In the last class we have discussed, and all the details explanation of solenoids I have given. There are 4 points, important points that you have to learn about the solenoid. Now we take the practical aspect of solenoid. You see here insulated copper wire is when wrapped over the insulating hollow pipe or cylindrical thing, then we get solenoids. And when the terminal of the solenoid is connected with the battery, then solenoid itself starts behaving like a bar magnet or a magnet. So you will see here the magnetic field is concentrated into a nearly uniform field in the interior or in the center of the long solenoid, and the field outside the solenoid is weak and divergent, but inside it is uniform. So you see from looking over the pattern, field line pattern here, you see that outside there is only one field line is showing here, but inside so many field lines are there. You see that field line enters into this terminal of the solenoid. Therefore, this terminal acts as a south pole, and field lines emerge out of this terminal, so it acts as a north pole. So this long solenoid behaves as a bar magnet with this end north pole and with this end south pole. You can say that with the end where current flows in the clockwise sense, this is called south pole, and where current flows in the anti-clockwise sense, it is called north. So this is the field pattern and it's called solenoid. So inside in the interior of this solenoid, expression for magnetic field is what? B equal to mu naught N I. Here mu naught is magnetic permeability that I have discussed so many times, permeability of the vacuum, and N is the number of turns of the coil per unit length, and I is here current. It means magnetic field inside the solenoid depends on number of turns and depends on amount of current flowing through the solenoids. So in this way we can increase or decrease the magnetic field inside the solenoid by increasing or decreasing current. Or even we can make a strong electromagnet using large number of turns of the solenoids. So one thing we have to remember once again, that in the interior of the solenoid, magnetic field is uniform and stronger. On the other hand, outside the solenoid, magnetic field is weaker and negligible. Just like inside the bar magnet, magnetic field was uniform and stronger. On the other hand, outside the bar magnet, magnetic field was weaker. So you see here, a strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside coil. The magnet so formed is called electromagnet. So you can say that if this is the iron rod and this coil is insulated, wrapped over this iron rod, when current passes through this coil, then this iron rod acts as a magnet. This iron rod will start attracting another iron nail and will start repelling or attracting another bar magnet as long as current flowing through the coil. If a strong, a large number of turns of the coil is there and high current flows through the coil, then this iron rod becomes magnetized permanently and will behave as a magnet. So solenoid can also be used for magnetizing iron or any ferromagnetic substance to have a permanent magnet. So you can see the here activities. This is the coil and this is the iron rod. As soon as in the coil current passes, this rod will start attracting the seizure, which is made up of iron itself. But as soon as switch is off, this iron rod becomes neutral and this seizure will fall down. So you see here, seizure fall down after disconnecting the coil with the battery, indicating that as long as current flows through the coil, only then this will act as electromagnet, and that's why iron rod attract the seizures. Now next concept, so far we have discussed about magnetic field due to current carrying conductor in various shape and magnetic field patterns or field lines. Now we will discuss about the another aspect of magnetic effect of electric current, that is when a current carrying conductor is placed or brought near a strong magnet, then current carrying conductor get attracted or deviated in presence of that strong magnet. But as soon as current is switched off in the conductor, then this deviation is not observed. So this indicates that a current carrying conductor experiences a kind of force when placed in a region of magnetic field. Now, so you have to see here force on current carrying conductor in a magnetic field, and aluminium rod AB is suspended between the pole pieces of horseshoe magnet as shown in the figure. This is aluminium rod, because you will see that aluminium rod is not attracted or repelled by the magnets. It is non-magnetic, that's why we have taken. But aluminium rod is a conductor, good conductor of electricity. That's why this aluminium rod is taken for observing this force, magnetic force acting on current carrying conductor. So here you will see that when current allowed to pass through this aluminium rod, then this rod will experience a force in this direction. It will get deviated in the interior of the horseshoe magnet, and when direction of current get reversed, it will experience a force reverse of that one, that it will repel outside the horseshoe magnet. So second point is that a current is allowed to flow through the conductor AB, aluminium rod, in the direction from B to A. You see here, B to A. The conductor is found to get deflected to the left side as shown by the arrow. You see here, it get deflected to the left side. Now, when the pole of magnet is interchanged, now you reverse the pole of the magnet. Say, north pole is reversed to this side and south pole is reversed to this side. then what will happen? In that situation, current is still flowing from B to A, but the force on conductor is found to be on the right side, that is in this direction. So it means that from these activities, whenever a current carrying conductor is placed near the external magnetic field or external magnet, the current carrying conductor experiences a force, and direction of force depends on the direction of current flowing through the conductor or direction of magnetic field or polarity. If polarity is changed, the force, direction of force would get changed. When the poles of magnet is interchanged and when the current is still from B to A, then force on the conductor is found to be on the right side, you see here. So here we have changed the polarity of the magnet, then direction of force get changed. Now in this section, we will fix the polarity of magnet, but will change the direction of current. Still you will see that the force acting on the magnet would change. So if current is now allowed to flow from A to B, that is reverse of this situation. That is, direction is reversed. Direction of current is reversed. Without reversing the pole pieces of the magnet, then deflection of conductor is to the left as shown in the figure. If direction is changed, then deflection of conductor will be towards the left, because it is south pole and it is north pole, so it becomes towards left. Now if the current is from A to B, that is direction is reversed, and also reversing the pole pieces of the magnet, that is this south is reversed to north, then deflection of conductor is to the right as shown. In this situation, deflection get reversed. So next thing is these four pictures were based on the activities that you can learn from activities, and even you can perform these activities at your home. Now force on current carrying conductor in a uniform magnetic field. So an electric current flowing through a conductor produces a magnetic field. It is well known to all of us. The field is produced, exert force on a magnet placed in a vicinity of the conductor. So magnet also exert an equal and opposite force on the conductor, and hence the magnitude of this force is highest when the direction of current is at the right angle to the direction of magnetic field. That means this magnetic force depends on orientation of conductor with respect to magnetic field, orientation of current with respect to magnetic field, or you can say that direction of electric current and direction of magnetic field. If current and magnetic field both are directed in the same direction, no force is experienced by the conductor. So to sum up, the direction of force is reversed when the direction of current through the conductor is reversed. That is, direction of magnetic force acting on current carrying conductor when placed in external magnetic field is reversed when direction of current through the conductor is reversed. Also, direction of force is also reversed by interchanging the two poles of the magnet. If the two poles of the magnet pole pieces interchange, also force direction get changed. You see here in this case, current flows from B to A, then force exerted in this direction. Here current flows from B to A, that means direction of current is same, but pole pieces is interchanged. so force direction get changed outwards. Now here pole pieces remain same, but direction of current is reversed, then force would get changed. That is reverse of this one. Now, if both direction of current and pole pieces changed, then direction of force will be changed. Now, direction of the force acting on current carrying conductor due to external magnetic field or external magnet is determined by the Fleming's left hand rule. So now we have to learn about the Fleming's left hand rule. You see here, first of all, we have to learn what is Fleming's left hand rule. You see, the direction of current, force and magnetic field can be illustrated through the simple rule called Fleming's left hand rule. And according to this rule, if the direction of current is at the right angle to the direction of magnetic field, then the direction of magnetic force will be perpendicular to the plane of the current and magnetic field. So here we have to learn the statement of the Fleming's left hand rule. According to this rule, if one stretch the thumb, forefinger and middle finger of his left hand in such a way that these three fingers are mutually perpendicular and forefinger pointing in the direction of magnetic field, middle finger pointing in the direction of current, then thumb would point in the direction of magnetic force. So you see here, the first finger points in the direction of magnetic field, that is forefinger points in the direction of magnetic field, and the second finger or in the middle finger pointing in the direction of current, then thumb will point in the direction of motion or in the direction of force acting on the current carrying conductor. So this is all about the Fleming's left hand rule. Now you can see here, hello, yes. One more thing that we have to learn about Fleming's left hand rule. Just wait.
Approximately 5-6 minutes.
Oh.